Today we're going to be talking about section 2.5, which is on how to model direct variations. So our goal is to write and graph direct variation equations today. So to start with, we need to look at what a direct variation is. And a direct variation in two variables, x and y, show direct variation provided that y equals ax, where a is the constant of variation. And it's going to be a non-zero constant, so it's going to not change. It's going to be some number, 4. So we'd have an equation like y equals 4x, or y equals 3x, or y equals negative 2x. So the constant of variation is the non-zero constant a in the direct variation. So it's y equals ax, and if you solve it for a, it would be a equals y divided by x. Now we may look at that later, or we will look at it later to tell if either a table or a set of ordered pairs is a direct variation. Because then we can look at when we divide, take y divided by x, does it give us the same constant? If it does, then that's a direct variation. So the constant of variation and in the direct variation equation, y equals ax. Make sure you have that on your note card. You're going to want to know that. So in example 1, we want to write and graph a direct variation equation. So write and graph a direct variation equation that has -3, -9 as a solution. So what we're going to do, I'm going to redraw my graph here along this axis. Actually, I'm not going to do that because I need to go the other one. So we're going to be So we're going to say this is 0, 0. Here's the origin. So -1, -1. So it says we're going to go to -3, -9. And then it's always, our graph's always going to go through the origin. Because when you think about it, there's your equation in slope-intercept form. Well, this looks very similar to this, y equals ax, only we don't have a y-intercept, which means the y-intercept is actually 0. So it's always going to go through the origin. So your graph of this was always going to go through the origin. So if we take our constant of variation, we're going to find that. So we're going to put in our -9 equals a times x is -3. So divide by -3. So we have a equals 3. So our equation is y equals 3x. Now, if we would look at this graph, we'd go up 1, 2, 3 over 1, up 1, 2, 3 over 1, up 1, 2, 3 over 1. So that, in fact, is the graph of that equation. So when we take this ordered pair, all we have to do is plug it into our direct variation equation. Find the constant of variation and graph it. So below here in the guided practice questions, we have 4 of them. Go ahead and just graph a couple of them. You don't need to do all 4. So go ahead and take a couple minutes to do those. Hit pause on the video, and you can hit play when you're ready to move on. And here are the answers for your guided practice questions 1 through 4. Notice in the first graph I went by 2s because I wasn't going to have enough room on there. You could on the other ones as well, but so there's your graph. We got the equation of each one, and then we graphed each one of them as well. Example 2 says we're going to write and apply a model for direct variation. So it says Hooke's law states that the distance d a spring travels varies directly with a force F that is applied to it. All right, so when we look at this, we want to come up what is the general direct variation equation. So it says that d varies directly with F. So those are the numbers that are that's the equation I'm going to use. Whatever varies directly is going to go on the left side with the force on the right side. So now it says for A, it says suppose that a spring stretches 15 inches, and that's the distance when a force F, that's the force, pounds of 9 pounds is applied. So write an equation that relates D to F. So again, we're going to put our 15 equals A times the 9, divide by the 9, and A is going to be 15 ninths. Well, we can reduce that, divide them both by 3, so we're going to get 5/3. And so our equation is going to be D equals 5/3 F. And so there is the direct variation equation for this situation. And then part B now says predict the distance a spring will stretch when a force of 6 pounds is applied. So all we have to do now is put in our numbers. 6 pounds, that's our F. And so we're going to get 30 divided by 3, which is 10. So now, again, this is the word problem. We need to make sure we know what D stands for. And if we look up here, D is the distance that a spring stretches. So we're going to say the spring will stretch 10 inches. All right, down to example 3, it says use a ratio to identify direct variation. The dimensions of 5 rectangles, each with an area of 24 feet, are given in the chart. Tell whether the length and width show direct variation. If so, write the equation. Now remember, our direct variation equation is y equals a over x. We want to know, is the constant going to be the same? Well, to do that, we're going to solve for a. So it's going to be y divided by x. So in this case, this is what we're looking at. If we take y divided by x in each of these cases, it'll be a direct variation. If not, then it's not. So here we have 24 divided by 1, which is 24. Here we have 12 divided by 2, which is 6. Right away, we get two different numbers. We don't have to go any farther. Okay? If there's any situation here where it doesn't work, other than using 0, then we know that this is not a direct variation. Okay, so in this case, it's not a direct variation. For this to be a direct variation, when we take y divided by x in every single one of these, it has to give us a constant. All right, so jumping to example or guided practice questions 5 and 6. They are in your book on page 109 right at the top. So go ahead and open your books page 109 and look at those problems. You can go ahead and pause the video and hit play when you're ready to move on. And here are the answers to the guided practice. In question 5, we're going to use the equation that they give us from the example 2 in the book, t equals 0.0625t, and then we plug in, and they tell us how long is it when the hailstone has a radius of 0.6 inches. Well, D stands for diameter, so we take 1.2, so that's twice of that, and we plug it in, and we find that it's been forming for 19.2 minutes. And then for number 6, they ask if this is a direct variation, and it is not a direct variation. Because if we notice, these ratios are not the same. Now, when we talk about a real-life situation, if you look in the book in example 3, in that shark problem, they have 6 of them, and they have Instead of 44.4, 91.7, 129.3, they get numbers of about approximately 119, approximately 119, a 121, a 120, a 121, and a 120. If they're very, very close like that, and it's a real life situation, then this would be a direct variation. They don't need to be exact in a real life situation just because there's going to be some measure of error. So make sure that you know that when we do the direct variations. So again, today, section 2.5, pretty short and simple. It's on how to model direct variation equations. Your equation is y equals ax, where a is the constant of variation. And you can plug numbers in for y and x and find what that constant is and then come up with how to graph it. So here's your homework assignment for section 2.5.